In the previous video, we saw the need to define groups of subtypes, since the transaction had a double reference to the same actor of reality. This was the case with the flight transaction, which had a departure and an arrival airport for each flight. We couldn't include the same attribute, airport ID, in the transaction structure twice, because GeneXus showed an error for adding a duplicate attribute name. For that reason, we decided to define two groups of subtypes: flight departure airport to identify the departure airport, and flight arrival airport to identify the arrival airport. Since we wanted to infer the country and city of each airport, in each group we also defined subtypes of the attributes corresponding to country and city, as well as the name of the airport. Therefore, when we name flight departure country name in the flight transaction, we know that it will be a country name inferred through the departure airport, flight departure airport ID. These subtypes have been defined within the same group, and therefore the association and relationship between them has been established. And when we name flight arrival country name in the flight transaction, we know that it will be inferred through the flight arrival airport ID attribute. That is to say, there is no ambiguity. There are two completely different ways to get to country from flight. Another option was to leave the airport ID name attribute for the role of the departure airport and define a group of subtypes to identify the arrival airport. Or else, leave the attribute named airport ID for the role of the arrival airport and define a group of subtypes to identify the departure airport. In both options, the data model will reflect the same relationships as in the previous solution. In the previous video, we then saw the case of multiple references from one table to another directly related to it. However, these references don't have to be direct. From one table, there can be two paths to another, as it's an indirect relationship, so subtypes will be needed to differentiate them. Suppose we have to add a transaction to record the information of the tour guides. Each guide has a specific nationality, and for that reason, we've added the country ID attribute to its transaction structure. If we look at the table diagram, from the attraction transaction, we can infer the country name corresponding to that attraction, since it's in an extended table. Likewise, from tour guide, we can also infer its own country name, that is, the guide's country. If we now link the attraction and tour guide entities by adding to the first one the attribute identifying the guide, tour guide ID, to indicate that a tourist attraction has only one guide assigned to it, how are the tables now related? Tour guide ID will be a foreign key in attraction to the tour guide table, so the relationship will be marked with the sky blue arrow. That may lead us to think that from attraction, there are now two ways to infer country name, which means that there is an ambiguity. In other words, since GeneXus has the country name attribute in attraction, where does it infer it from? From the attraction city or the attraction tour guide? If both values were the same, it wouldn't matter, but in this case, they don't have to match. The country where the attraction is located doesn't have to match the tour guide's home country. In order to differentiate both country name roles, we will need to use subtypes. But in this case, we will not only need them to differentiate the roles. Let's look at the table diagram after adding the tour guide ID attribute in the attraction transaction. The relationship between attraction and country city disappears, as country ID is no longer a foreign key in attraction. Note that it's no longer in the table. That is, it'll be an inferred attribute. But inferred from what? From tour guide ID. Remember that GeneXus first normalizes the tables. That is, based on the attribute names, together with the identifiers, it determines which attribute is placed in each table and the relationships between them. As tour guide ID is shown in attraction, that is, the tour guide identifier, and at the same time, country ID is shown in tour guide, the country identifier, It understands that given a tour guide ID and attraction, the country name is inferred from it, going through the tour guide intermediate table. Therefore, with this transaction design, we can't indicate which is the country of the attraction because the country name will be that of the tour guide. We have no choice but to use subtypes in order to make attraction have its own country, independently from the country of the tour guide. We'll create a group of subtypes to represent the country and city of the attraction, since it's attraction where the problem occurs. Note that now GeneXus correctly represents the relationships in the table diagram. In addition, the country name attribute is now inferred from tour guide ID without ambiguity. The attribute that represents the attraction country and from which it's inferred will be the one called attraction country name, a subtype of country name that belongs to the group attraction country city. Also note that this group has two primary attributes, attraction country ID and attraction city ID, which correspond to the primary key of the country city table, according to the supertypes indicated, country ID, city ID. This solution solves the problem. But we must take into account that if there are other objects that already use the original attributes, country ID and country name, to search for the attraction country, we may have to modify them in those objects and use the subtype attributes, attraction country ID and attraction country name respectively. There are other possible solutions that will not be studied in this course. Now let's take a look at another case of use of subtypes, which we call specialization, in which there's a transaction that records general information, and then there are transactions with particular information, which are a specialization of that other one. Suppose that the travel agency needs to handle specific information about the customers to whom it sells tickets and tour packages. For example, their taxpayer number at the state tax office, if any. Specific information about the passengers, for example, their passport number and validity. And also specific information about the agency's employees, for whom it must record, for example, their salary. In other words, the travel agency will invoice customers, provide seat reservations for passengers, and issue pay slips to employees. So, instead of just a customer transaction, we could define a transaction called person that handles information that is common to all people. For example, a name, date of birth, address, phone number, and so on. And transactions that are person specializations, because customers, passengers, and employees are people. Each specialization will have its own specific data. Customer will have a taxpayer number. Passenger will have a passport number and expiration date. And employee will have a salary. We want the customer ID to exactly match that of a person to reflect that the customer is a person. That is to say, if the person with ID 8 is called Ann Roberts, and she was born on 5/5/1970, when entering her information as a customer, the user needs to be able to type the ID 8 in the customer transaction. Also, when leaving the field, the name Ann Roberts should be shown in order to enter the taxpayer number in the customer taxpayer ID attribute. Likewise, if the passenger transaction is executed, when the user types the value 8 in passenger ID, we want Ann Roberts to be inferred in passenger name, and the user to be able to assign the passport number and expiration date in the specific attributes, passenger passport number, and passenger passport expiration date, and for the employees as well. If we simply define as primary keys of customer, passenger, and employee, the attributes customer ID, passenger ID, and employee ID respectively, without relating them in any way to person ID, such as customer name, passenger name, and employee name, without relating them to person name, we will not get what we're looking for. For GeneXus, they will be completely independent transactions. So to relate them, we're going to define groups of subtypes to indicate that customers, passengers, and employees must be valid, in other words, previously registered, persons. We create a customer person group, where we define customer ID and customer name as subtypes of person ID and person name, respectively. Also, another one called passenger person, where we define passenger ID and passenger name as subtypes of person ID and person name, respectively. And lastly, a group called employee person, where we define employee ID and employee name as subtypes of person ID and person name, respectively. By doing this, the attributes customer ID, passenger ID, and employee ID, besides being the identifiers of the customer, passenger, and employee tables, respectively, and therefore their primary keys, will also be foreign keys of the person table. In this case, GeneXus will control the consistency of the data. This means that when the user enters a value in the ID of any of the three transactions, customer, passenger, or employee, a record with the same ID value will be searched for in the person table. Similarly, if we want to delete a person through the person transaction, it'll be checked that there is no record in customer where customer ID matches the person ID that we're trying to delete. Or a record in passenger where passenger ID matches the person ID to be deleted. Or a record in employee where employee ID matches the person ID to be deleted. If any of these three records exists, we will not be allowed to delete the person. This design represents one-to-one relationships between the general table and the one corresponding to each specialization. That is to say, a person can only be registered once as a customer because customer ID is a valid person ID and is also a primary key. Likewise, a person can be registered only once as a passenger and only once as an employee. A person can have all three roles or be registered only as a person and have no additional data as a client of the agency, as an employee, or as a passenger. In the customer, passenger, and employee transactions, customer name, passenger name, and employee name will be inferred attributes, so they won't be physically stored in the tables customer, passenger, and employee, respectively. Remember that the diagrams created by GeneXus don't show one-to-one relationships, and the arrows only indicate foreign key relationships. That's why we see the double arrow next to the specialized tables. There are other cases of use of subtypes that will not be studied in this course. If you're interested, you can look for information related to this topic in the next level course.